In the vast, silent graveyards of our universe, there exist objects that defy the very laws of nature. They are not quite stars, yet they are far from dead. Meet the neutron star, one of the most extreme objects in the cosmos. A sphere the size of a small city, yet it packs more mass than our entire sun into a space just 20 kilometers wide. A neutron star forms when a massive star exhausts its internal fuel. Without the outward pressure of fusion, the core collapses under the force of gravity in a fraction of a second. This rapid contraction triggers a supernova, an explosion that expels the star's outer layers into space. What remains is the exposed core. What remains in the wake of this cosmic debris is a neutron star, one of the strangest and most dense objects in the universe. Wrapped in a magnetic field trillions of times stronger than Earth's, acting as a ghostly lighthouse in the darkness of space. A single teaspoon of neutron star material would weigh over 1 billion tons, roughly the weight of a literal mountain. At the moment of its violent birth, a neutron star's core can reach up to a temperature of 1 trillion degrees Celsius. For a brief window of time, it is the hottest point in the known universe. However, this extreme energy is unsustainable. Through a rapid release of neutrinos, the star cools at an impossible rate. Within days, the temperature drops to 1 billion degrees, and after a few thousand years, it settles into a calm state of 1 million degrees Celsius. Depending on their environment and the strength of their magnetic fields, neutron stars exist in different forms. One is pulsars, the cosmic lighthouses. These stars spin hundreds of times per second, blasting beams of radiation from their poles. Then there are the magnetars, the drama queens of the cosmos. These possess magnetic fields 1,000 times stronger than a typical neutron star. They are so unstable that their crusts can crack, releasing starquakes that blast out more energy in 1/10 of a second than our sun does in 150,000 years. The third type is the accretion-powered neutron star. These stars don't live alone. They exist in a binary system with a donor star. Using its immense gravity, the neutron star pulls layers of gas away from its companion, spiraling them into a glowing disk. The atmosphere of a neutron star is crushed into a few centimeters. It consists of a pressurized layer of hydrogen, helium, and carbon. Deeper down, the outer crust of ions and electrons gives way to an inner crust filled with a frictionless superfluid of neutrons. In the outer core, protons become superconducting, generating the star's massive magnetic field. But at the very center, the inner core, the state of matter remains unknown. While the sun's gravity is 28 times stronger than Earth's, the pull on a neutron star is 100 billion times greater. Therefore, we can see the phenomenon of time dilation here. When a star much larger than our sun reaches the end of its life, it detonates in a supernova, leaving behind a choice. If the star's core is between 1 and 3 times the mass of the sun, gravity is held at bay by the sheer pressure of neutrons. The result is the neutron star, a city-sized titan that sits at the very edge of what physics allows to exist. It is a world of superconducting protons and mysterious fluids, fighting an eternal war against its own weight. But for the true monsters of the cosmos, there is no such balance. If the dying star is massive enough, not even the density of an atomic nucleus can hold back the crush. The core continues to fall inward, faster and faster, tearing the fabric of space-time until the star literally collapses out of existence. In its place, it leaves a black hole, an infinite abyss where gravity has finally won its battle, and the universe itself is pulled into a point of no return.